Hola, les doy la bienvenida al podcast de la Asociación Mexicana de Adsorption. Yo soy Nancy Dávila, profesora de la Universidad Autónoma de Nuevo León y presidenta de la asociación. Hoy hablaremos sobre caracterización de adsorbentes microporosos. Específicamente hablaremos de la determinación del área superficial y de la distribución de tamaño de poro. Te invito a que me acompañes a escuchar esta plática con el doctor Francisco Sotomayor, quien es gerente de producto de analizadores de absorción de gas para Anton Paar, Quantatech, anteriormente Quantachrome Instruments. El doctor Sotomayor es experto en el área de caracterización de materiales, específicamente en métodos de análisis para determinar características físicas de materiales y aplicaciones de absorción y separación de gases. El doctor obtuvo su grado en Ingeniería Ambiental por la Universidad de Michigan, centrando su tesis doctoral en el estudio de materiales microporosos flexibles en aplicaciones de separación de gases. Bienvenido, doctor Francisco Sotomayor. Muchísimas gracias por acompañarnos.
Yeah, thank you, Nancy, for having me today. Happy to be here. Looking forward to talking with you and your audience about Gasorption and the characterization of porous materials.
Muchas gracias. Bueno, pues una de las características físico-químicas más importantes de los materiales adsorbentes y de los catalizadores es el área superficial. Me gustaría que comenzáramos esta charla introduciendo a nuestra audiencia sobre este concepto, qué es el área superficial y por qué es importante en los procesos de adsorción.
Sure, I think that's a great place to start. So I think most people are familiar with the concept of area, in their everyday life. For example, like the area of a soccer field or the surface area of like a three-dimensional cube. But I think most people don't think about these things from the perspective of a small gas molecule. So what you see as a perfectly flat surface, of a table or of a soccer field, from the perspective of a person, is actually a very rough surface when you look at it from the perspective of a gas molecule. There are peaks and valleys due to the roughness of the surface. There can be cracks or pores in the surface, which gas molecules can enter. And it's really this roughness at that molecular level, which we sometimes call the probe accessible surface area, that we are really interested in when it comes to gas adsorption. So the total surface area, including the molecular level surface roughness, is what controls things, sort of any interaction between the solid and its surroundings, whether those surroundings be gas or liquid or other solids. It affects things like the rate of dissolution of powders, the rate of reaction on catalysts, the storage capacity for adsorbed gases. So it's very important for us to understand and measure this surface area at the molecular level of our materials.
De acuerdo. Ahora que establecimos la importancia del área superficial para estos materiales adsorbentes, platiquemos acerca de los métodos para estimarla. ¿Cuál es la técnica más utilizada para determinar el área superficial de un adsorbente y en qué consiste?
Yeah, so there are many techniques people have used over the years to get an estimate of surface areas. You can get an estimate of the surface area from particle size measurements, mercury porosimetry. You can even get an estimate of it from experiments of air permeability flowing through powder beds. So lots of different techniques have been used over the years. But one technique in particular has been widely and very effectively used for adsorbent materials. And that's the technique of gas adsorption. So when we talk about gas adsorption for surface area measurements, it usually involves introducing the sample to an inert gas like nitrogen or argon or krypton at cryogenic temperatures, so very, very cold, something like 77 Kelvin or 87 Kelvin. And then we measure the amount of adsorption of that gas that occurs on the surface of the material at some specific pressures, right? And the amount of adsorption and the pressure at which it occurs is going to be directly related to the surface roughness and the porosity of that adsorbent material. So some of the benefits of Gasorption is that it allows for kind of probing the entire surface, including any of those pore interiors or cracks in the surface. As long as the area is accessible to your probe molecule, your gas molecule, it's going to be included in the area reported by this technique. And the results are going to be an average representation of your entire sample, not like a snapshot or a picture of just a small area. So it's a very powerful technique, and it's especially important in the context of adsorbents or catalyst materials, because they are often used in applications where they're treating pollutants or reactants that are also these small molecules that can enter into those crevices and pore structures. So it's not enough to only understand or know the external area of the particle or just the particle size. Really understanding that total probe accessible surface area and porosity is going to be really important in these applications.
Con respecto a los modelos matemáticos que se utilizan para analizar los datos experimentales que posteriormente nos van a permitir estimar el área superficial, ¿podría decirnos cuáles son los más reportados en la literatura y si estos modelos matemáticos son aplicables a todo tipo de material adsorbente?
Sure. So similar to the wide amount of techniques that I sort of mentioned in the previous section, that allow us to explore surface roughness and porosity, there are a large number of mathematical models and methods that can be used with Gasorption data to get surface area. But I would say that the method of Brunauer, Emmett, and Teller, or the BET method, is by far the most commonly used for the determination of specific surface area. It is still considered state-of-the-art, even though it was actually derived over 75 years ago. In fact, a lot of users of Gasorption instruments refer to the instruments as, BET instruments, even though gas adsorption as a technique includes many more methods than just the BET method. The nice thing about the BET method is that it uses, or it is derived from kinetic theory, but accounts for multiple layers of gas molecules adsorbing on the surface. So this multi-layer adsorption assumption is more closely matches the real behavior of physically adsorbed gas molecules on solid surfaces. And it's a little bit better of an assumption than some of the other theories to calculate surface area, like the Langmuir method, which assumes just a single layer of gas molecules adsorbing on a flat surface. So the BET method has been used very successfully and actually can be said to give the true probe accessible surface area of a lot of materials, especially those non-porous or macroporous materials. It's also quite easy to do with the right equipment, so it's very popular for characterizing newly synthesized materials and widely cited in the literature. There is one drawback of this method that I want to mention, which is that it does assume that the surface is flat or flat enough from the perspective of a gas molecule, right? That's not a problem for most everyday materials, but when we talk about the BET surface area of porous materials, especially those that have the very smallest pores, those microporous materials, we should recognize that the BET area is more of a representative area that is characteristic of the material and not necessarily the true probe accessible surface area.
Ok, muy interesante. Otra característica físico-química que es muy importante de los materiales adsorbentes es su porosidad. Y de acuerdo a la UPAC, hay una clasificación, ¿verdad?, para cada uno de estos tipos de materiales. ¿Nos puede comentar cómo se clasifican los materiales porosos?
Yeah, so in the context of gas adsorption, we can generally define porous materials by the size of their pores, that is the pore widths. So we can subdivide materials into those that are what we call macroporous or non-porous. So those are materials that have pores that are greater than 50 nanometers in size, which when you think about those sizes from the perspective of a gas molecule, they're so large that they're really not that much different from a flat surface, right, from the perspective of a gas molecule. Then you can look at mesoporous materials, or those having medium-sized pores between, say, 2 and 50 nanometers, and then even smaller into microporous materials, or those having pores less than 2 nanometers. right? And some people will further divide microporous materials into what are called super micropores, or pores having sizes between 0.7 and 2 nanometers, and ultra microporous materials having pore sizes less than 0.7 nanometers.
Okay. ¿Cómo podemos estimar la porosidad de un material adsorbente?
Yeah, so there's a number of techniques you can use depending on whether you are simply interested in, say, the total pore volume or the micropore volume, or if you would like to account for the pore size distribution of the material, the distribution of volumes according to pore size, right? People have used a combination of things like mercury displacement and gas manometry, for example, but for this conversation, I think we can focus on just Gasorption again. So similar to how you can cover the surface of the material with gas molecules and get a measure of that surface area, we can also drive the pressure high enough to completely fill the pores of the material with gas molecules. And depending on the amount of gas that fills the pores and the pressure that's required to fill the pore, you can determine the pore volume and also the pore size distribution of the material. There are simple calculations available, like the Gervich rule that allow you to determine the total pore volume, or more complicated methods like state-of-the-art DFT methods, which can give you complete pore size distributions from, say, 0.35 nanometers up to 100 nanometers or more. Right? So gas adsorption really is an incredibly flexible technique for understanding the physical characteristics of your material surface.
Exacto. Bien, en los últimos años sabemos que han surgido nuevos materiales microporosos con elevadas áreas superficiales. Como ejemplo, podemos mencionar los armazones organometálicos o MOF, por sus siglas en inglés, ya que de estos materiales se han reportado áreas superficiales superiores incluso a los 7,000 metros cuadrados por gramo. ¿Cómo se pueden estimar estas áreas superficiales tan elevadas? ¿Y qué buenas prácticas nos puede recomendar para evaluar el área superficial de este tipo de materiales?
Yeah, so MOFs are a fascinating topic, actually. So I did my PhD research in elastic layered metal organic frameworks for gas separations applications. So I definitely have a special place in my heart for MOF materials. And I highly recommend that everyone have their own favorite MOF because there's so many to choose from. But one thing that I like to say is that these are new materials. They've only been around for a few decades now, and because they're so new and the types of structures are so varied, a lot of people sort of misunderstand how to interpret the results of Gasorption experiments for MOFs. So when we see these like papers that report a surface area in the thousands, 1,000, 2,000, 3,000, 7,000 meters squared per gram, typically what they're reporting is that BET surface area result that we talked about earlier. If you remember what I mentioned earlier, that the BET method assumes that the material is close to a flat surface, right? And the interesting thing about MOFs is that they're actually very far from a flat surface. If you think about the crystal structure of many of these MOFs, it's this really open cavity space that's built using this skeletal framework of organic linkers and metal clusters. And in such an open framework, you don't really have walls or surfaces from the perspective of gas molecules. You just have this open space when this occasional like organic linker molecule, and that organic linker molecule might only be like a few atoms wide, right? So that's not really something that we can consider like a true external surface area the way we would typically picture it in sort of a non-porous material, right? So when someone reports a BET area for MOFs, what a lot of people fail to realize is that it's actually it's not really the true probe accessible surface area. It's more of a characteristic or representative value that's representing the porosity of the material. So many of these materials are incredibly porous, and that shows up as a very high surface area value, right? This is not to say that the BET area is not helpful to measure. It's still really valuable to to report the BET surface area to compare results between laboratories and to compare materials. But I think your listeners would do well not to sort of overinterpret the results from the BET method when it comes to novel framework structures like MOFs, because we're often applying it in a way that's not really consistent with the underlying assumptions of the theory of the BET.
De acuerdo. Pero como usted menciona, nos sirve de comparación, ¿no? Para ver con otros materiales y otros estudios.
Sí.
Algunos de los MOF presentan una estructura flexible. Seguramente quien trabaja en esta área o está comenzando a trabajar en esta área ha leído, ha escuchado referirse a algunas de las estructuras como con esta característica, ¿no? De ser flexibles. ¿Podría explicarnos qué significa esta propiedad y qué implicaciones puede tener en la estimación tanto de su área superficial como de la distribución del tamaño de poro?
Yeah, this is a great question. So I think this flexible nature of MOFs is definitely one of the more interesting aspects of a lot of these MOFs. So what do we mean by flexible? So generally, when we think of a crystal structure, we think of this rigid network where all the atoms are in a fixed sort of repeating pattern. The interesting thing about flexible MOFs, which sometimes are called like soft porous crystals, is that if you expose them to external stimuli like heat or light or magnetic fields or even different adsorbed gas molecules, that crystal structure can undergo a large structural change, changing the pattern of the structure without breaking the network connections. So you have these really interesting phenomenon like breathing effects or gating effects that people see in different applications with MOFs that you wouldn't see in like a classical rigid structure like an activated carbon or a zeolite type material, right? The challenge of characterizing these soft porous crystals is that the structure is not fixed. So you may have a MOF, for example, that under the conditions of our BET measurement, say nitrogen adsorption at 77 Kelvin, has no porosity, has very little surface area, but under a different set of external conditions, for example, in CO2 atmosphere at 273 Kelvin, this crystal structure suddenly opens up and has this huge porosity and large exposed surface area, allowing that material to absorb a huge amount of CO2, but not necessarily have any adsorption capacity for, say, nitrogen. This leads to really strange artifacts in adsorption isotherms like low pressure or open hysteresis, or even unexpected negative adsorption where the sample is suddenly releasing gas instead of absorbing it, right? So this means that many of these flexible MOFs are actually very difficult to characterize physically using sort of classical techniques. And to characterize them sort of adequately, you can't just rely on just a single surface area value or just a single pore size distribution. You're likely to end up with some sort of artifact in your measurement. So really, when we look at characterizing these flexible MOFs, we have to think about sort of combining a number of different techniques and different gas absorption experiments to really understand the physical nature, the behavior, and the application of these materials. So I've seen researchers go to the lengths of combining, say, a gas absorption measurement with an in situ XRD measurement at the same time, exposing the sample to different pressures of gas and then doing individual XRD measurements to really understand like the structural transitions of these materials. So very interesting topic for sure.
Sí, mucho que hablar de ese tema.
Sí.
Bien, ahora que comprendemos la importancia de la determinación de estas propiedades texturales de los adsorbentes, así como las técnicas y métodos adecuados para hacer estas mediciones, pues solo nos queda, pues ahora sí que contar con un equipo adecuado, ¿verdad? Un equipo de laboratorio que nos permita estimar estas propiedades, que sea confiable, que sea de alto rendimiento, que sea asequible. Me gustaría que nos contara lo que podemos encontrar en Anton Paar y cómo es que puede ser un gran aliado para la caracterización de nuestros materiales adsorbentes y catalizadores.
Sure. So Anton Paar is a global company owned by the charitable Santner Foundation and it's dedicated to the production and distribution of highly accurate laboratory instruments and process measuring systems. So for decades, Anton Paar has invested around 20% of its turnover into research and development and precision manufacturing. And so we now have a pretty wide range of analytical instruments and automation solutions. So we have solutions for density, rheology, microwave digestion, particle sizing, even atomic force microscopy, right? In 2018, so about 3 years ago, Anton Paar purchased Quantachrome Instruments, which is a company with more than 50 years of experience in Gasorption measurements. And through this new production subsidiary called Anton Paar Quantitech now, we offer a full suite of analyzers in surface and pores, covering things like solid density, surface area, pore size analysis, using a variety of techniques like gas adsorption, gas pyknometry, mercury porosimetry, and capillary flow porometry. So we're really a one-stop shop for the characterization needs of your laboratory for your adsorbents.
Perfecto, ¿no? Pues definitivamente tienen una gran variedad de equipos que nos pueden servir para la caracterización físico-química de nuestros materiales. Muchas gracias por compartirnos eso. Y bueno, pues muchas gracias nuevamente, doctor Francisco, por esta plática tan interesante en la que estoy muy segura que la asociación pues sentirá que es de gran interés para nuestros asociados. Lo invito a que nos dé un mensaje final de despedida, doctor. Adelante.
Yeah, so thank you for having me. It's been my pleasure to chat. Happy at all times to talk about Gasorption and characterization of porous materials. For listeners that are interested in reaching out to Anton Paar, I encourage them to talk with our local subsidiary in Anton Paar, Mexico. We have central offices in Hidalgo State near Pachuca City. We have regional offices in Mexico City and Monterrey. We also have technical support in Valle de Mexico, El Bajío, and El Noreste. And you can reach Anton Paar Mexico's phone number at, say, 55-8502-6001. You can also visit our website at antonpar.com or follow Anton Paar Mexico on LinkedIn for the latest news and updates.
Perfecto, muchas gracias. Esperamos poderlo tener pronto con una plática más sobre, más específica, ¿no? Sobre este tipo de materiales y cómo estimar estas propiedades para materiales microporosos como por ejemplo los armazones organometálicos. Nos encantaría escucharlo.
Yeah, it would be my pleasure to come on again.
Gracias. A nombre de la Asociación Mexicana de Adsorpción, los invito a seguirnos en nuestras redes sociales, en Twitter como @amda-mex y en Facebook como Asociación Mexicana de Adsorpción. El calendario de eventos lo encontrarán en nuestra página web www.adsorpcion.com.mx. Nos escuchamos en el próximo episodio. Muchas gracias.